Now, I'm going to leave this thing beeping. It'll beep the whole time, but at least that way I can record it and it gets the sound. I've been having trouble figuring out how to record these sessions since we started going to the telephone. But if this isn't too annoying, I found that I pretty much can block it from my mind listening to that beep. Okay. So just kind of looking up top here, I hadn't noticed this before. Oh, sorry, I didn't realize you weren't in the room yet. Okay. Can you see my screen? Okay. So this goes through the grades and the possible algebras that you might be taking, huh? So 8th grade is geometry. Is that what this means?
That's an add.
Oh, okay. So that's just, that doesn't have anything to do with your core curriculum or anything. All right.
Something I think you might want to work on today. Probably because the algebra teacher said that's what we're working on.
Okay, I talked to your mother briefly, and she mentioned that, is that you guys were getting into probability and something else, I forget, but so that's fine. If you've got stuff to work on, always let's do that. You got some problems for me?
Well, isn't there some on the book?
Okay, yeah, we can go back to the regular book, I guess. Yeah, so this middle one here. And what chapter are we on here?
No, not on this one, on the purple book.
Chapter 9 is probability. The purple book. The Algebra 1 book?
Yeah.
We can look. No, it doesn't. Well, hold on. No, they don't get into probability in Algebra 1, apparently. At least not in this book here. So we'll need to go back to the book that did have probability. And it looks like it's Chapter 9. And let's see. It's actually got quite a bit of probability in here. Does this correspond to what you've been doing in class?
No.
How can we go over what you're doing in class on probability?
Well, we're not doing anything.
You're not doing problems? Like if I said there's 4 red marbles in a jar and 5 blue marbles, and you draw a marble at random, what's the odds of getting a red marble?
Red marbles? Sorry.
It's okay. There were 4 red marbles.
4 red.
And 5 blues. They're in a jar. And I'm blindfolded and I reach in and pull out a marble. What's the odds that it'll be a red marble?
4 out of 9.
Yeah, 4 out of 9. Probability is the odds of success divided by all of the possible outcomes. Well, there's 9 possible outcomes. You could draw 1 of 4 reds or 1 of 5 blues. All right. It's going to be hard for me to cover probability just on my own because there's so many different levels of it, and I have no idea how deep you're getting into it. on its simplest level, probability is pretty simple. And we can look at what this book has. Let's see if this agrees with the stuff you've been doing. Number 1 there, where it says spinning an even number. What would be the odds? They don't even ask that. They find what's the favorable outcomes?
So, which one is most likely to happen?
No. When it says they're looking for spinning an even number. In other words, if I spin the thing on that wheel and it randomly falls on any slot, kind of like Wheel of Fortune.
So is favorable outcome same thing as the probability?
Well, they're making it harder than it needs to be. Yeah, let's go through it. Here, let me reduce this a little bit. Favorable outcomes would be the numbers, what? 2, 4, 6, and 8. As far as this spinning an even number. So there's 4 favorable outcomes. How many total possible outcomes are there?
9.
So 4/9 would be the odds of spinning an even number. Okay. What are the favorable outcomes that the number would be divisible by 4? Which of these numbers is divisible by 4? That's 1. What else?
8.
So there's 2. 2 outcomes that are favorable. What's the odds of spinning a number divisible by 4 going to be?
2 out of 9.
Okay. And a number greater than or equal to 3. Let's list them. What are all the favorable outcomes?
3, 4, 5, all the way up to 9.
How many is that?
And so, 7 out of 9.
Not very hard, is it? Probability on a simple level like this is very easy. But believe it or not, probability can be some of the most challenging math that I know. And I've been around it all my life. Probability can be really, really difficult. I don't know if you'll ever take a full probability and statistics class in high school. You might in college. You might in high school. They offer one. But it can definitely be challenging. I don't know if it's as challenging as calculus, but okay. So we randomly choose a butterfly. Find the number of ways the event can occur. How many ways can we choose red?
2 times because there's 2 butterflies?
Because there's 2 red butterflies. How many total butterflies are there?
7. So 2 out of 7.
Okay. About brown?
0 out of 7 because there's no brown.
How about choosing not blue?
4 out of 7 because there's the blue and a 7 of 3.
Yeah. We're liable to be to our algebra here very quickly today. Because at this level, I don't think you're going to have any problem. You randomly choose one push pin from the jar, determine the theoretical probability of the event of choosing a yellow pin, given this is what is in the jar, over here on the right.
So, first we have to sum all up.
Okay? Okay.
10 out of 40, meaning that there's 1 point.
Okay.
So
How about not choosing a blue?
My sister's computer just fell asleep.
What happened?
Things not going on. It just fell asleep.
Oh, so you can't see my screen anymore?
Yeah.
Okay. Push the space bar.
Okay, now it just turned itself off. I think it's...
You want to reboot and log back in?
Yeah. I will go get her charger.
Oh, you're on a laptop and the charger's going down.
Yeah.
Okay. You don't even need the reboot. Just go ahead and go get the charger and I'll just wait. Okay, so if you plug in the computer to the charger and into the wall, it should get that computer to start. Did the computer die totally? Did it turn itself off?
Yeah.
Yeah, so just turn it back on and plug it in. Or plug it in first and then turn it back on. Okay. So out of these 40 pins, there are 4 blue ones. So what is the odds of not choosing a blue pin?
1 out of 10.
No. The odds of not choosing a blue pin.
30 out of 10.
36. In other words, there are 36 pins that are not blue. There's 12 green, 6 white, 8 red, and 10 yellow. Okay, so the odds of not picking a blue one means the same as the odds of picking anything that isn't blue. One of the things about probability that's really important to understand is that the total odds are always equal to 1. The probability of something happening is never greater than 1. In other words, if something is certain to happen, like the Broncos losing to Seattle in the Super Bowl, that's the odds of 1. I was trying to be funny. If you're a big Bronco fan, that probably wasn't very funny, huh?
I don't really...
No, you're not a fan? Well, good, because you wouldn't have enjoyed the Super Bowl. Let me know when you get back into the meeting, or let me know when you can see my desktop. Now,
my sister has a password on her computer.
Okay. I'm going to go get her to...
Let me call her. She's at the bank with my mom.
Oh, okay. Okay. You need, can you call her on a different phone than the one we're on?
Yeah.
Okay.
Let's put you on speaker for a bit.
Okay. Now I've got you still logged in to go to meeting. It may just be, you may have to turn the computer on and you'll still be in. You don't need to? In other words, I'm not sure what you're going to find when you get the computer back on. I'm surprised that you're still logged into the meeting. I would have thought that it would have taken you out of the meeting instantly the moment her computer shut down.
Yeah, so apparently numbers and symbols are off in the password. Something is weird.
Your password isn't letting you get back in?
No, yeah, I got my sister's password, but now it's not letting me put the password in. I think I got it.
Incidentally, David, I wanted to offer you the same thing that I offered Sarah. If you ever feel like you would prefer to do a couple of half-hour sessions a week rather than one-hour session, that's fine with me, and it might be more preferable for you. I didn't mean to offer that just to her. Something you can think about if you ever decide you'd rather do that.
Yeah. Okay, so I'm back on.
Okay, good. So you can see my screen?
Yeah.
Okay, let's talk about this principle I was just talking about. There are 4 blue pins in there. So the odds of picking a blue pin are 4 out of 40, right?
Yeah.
So if I want the odds of not picking a blue pin, it's always going to be 1 minus that. In other words, the total odds of anything happening are always 1. I either have to pick a blue pin or I'm going to pick a pin that's not blue. Those probabilities have to total 1. Notice that the odds of picking a not blue pin are 36 over 40. If I add that to 4 over 40, I get 1. But rather rather than having to count up the number of non-blue pins, I can just take the number of blue pins and subtract that number from the number 1. If I said that there was a 75% chance of snow tomorrow, what's the chance that it's not going to snow tomorrow?
25.
Yeah, they always total 1. In other words, when you include all possible scenarios, it totals 1. Now, I suppose you could say, well, maybe a meteor will hit the planet tonight, and it won't do either, but I guess that would qualify as not snowing. So that's an important principle with probability, is that all possibilities total 1. Because a lot of times when they say, what's the odds of not getting a blue, let's just say that there's 15 colors and so many pins that I don't want to count them all up. So instead of counting them all up, I would just say, well, 1 minus 4 over 40 is the easier way to come up with that answer. What's the odds of choosing a green or a red pin?
So 40 total, and then 6 plus 8 equals...
Green or red?
Oh, green or red. Oh, sorry, that's right. So 1 out of every...
Good. Is this pretty much the same kind of stuff you're doing in your class? Okay. The spinner is spun. Determine if the game is fair. If it is not fair, who has the greater probability of winning? You win if the number is even. Your friend wins if the number is odd. How many ways do you have to win?
It is fair because every other number is even, and then every other number is odd.
So there's the same number of evens as there is odd.
Yes.
If I go back and ask the same question on this wheel up here, is it a fair game?
It's not a fair game because there's not as many evens.
There's 5 odds and only 4 evens. So your friend would have a greater likelihood of having an odd number come up on this wheel than this one. He would have about a 54% chance up here, but he's only going to have a 50% chance here. Okay, you win if the number is less than 4. Your friend wins if the number is 4 or greater.
That is not fair because if the number is 4 or greater, that means that he has a 5 out of 8 chance.
Okay.
More than a 50% chance.
Well, actually, your chance is only 3 out of 8. Because you only win if the number is less than 4, which means it has to be 1, 2, or 3.
Yeah, that's what I said. My friend has a 4 out of 8.
He has 5 out of 8. You would have 3 out of 8.
That's what I meant. Sorry.
Okay. Number 12. The theoretical probability that your ticket will be drawn from a bucket to win a bicycle is 1 over 35. If there are 665 tickets, how many tickets are yours?
1 out of 35.
What equation can I set up that I can solve?
1 out of 35.
About 1 over 35.
Equals x over 665.
There you go. It's a straight ratio problem. So x is 665 divided by 35, which is 19.
19 of the tickets.
You know how I did that so quick? Well, 35 times 20 is 700, right? Notice that 665 is exactly 35 less than 700. So it has to be 35 times 19. Without doing any math. I mean, I had to do some math, but I did not have to do this math. I did not have to do it like this, which would be the normal way of doing it. That's actually much tougher to do, the long division, than it is to do the shortcut. It's always worth looking for shortcuts like that because you can do stuff so much faster. And they'll usually give you, in other words, I had a strong suspicion. First of all, I knew x had to be a whole number. In other words, there's no way that 665 divided by 35 is a fraction or a mixed number. It's going to be a whole number. So I knew that there was probably a shortcut for doing it. All right, let's see. There are 104 apples in a bushel. Probability of choosing a Granny Smith apple is 25%. How many apples are not Granny Smith apples?
So 104 divided by 4
Okay.
equals 21.
Okay. So there's go ahead.
104 minus 21 equals 83.
That's how many are not Granny apples. All right. Let's see if we can, what experimental probability has to say. What they mean by experimental probability?
Is that you try it out?
Yeah. Say, I wanted to know what's the probability that you're going to make a free throw on a basketball court.
So I should do like 50 or 20 or 10 free throws.
And record your results. The more you do, the higher the accuracy is going to be. In other words, if I only recorded 2 free throws and you made one and missed one, I'd be tempted to say, well, you have a 50% chance of making one. But if you took 10 shots and you made 3 and you missed 7, now I would say, well, you have a 30% chance of making it. And the 30%'s a better prediction because it's based on more experiments. If you took 100 free throws and you made 32 of them, then I would say your experimental probability is 32%. So experimental probability is just that. It's when you don't know what the exact odds should be. So you record results and you let that approximate the probability. Let's say you didn't know how many marbles were in a jar. And somebody said, well, there's only blue and red marbles in there. And I said, well, blindfold yourself, reach into the jar and pick out a marble and do that 10 times in a row. Well, if half the time you picked the blue marble and half the time you picked a red marble, you'd be inclined to say that the jar is half full of reds and half blues. If 9 times you picked a blue and 1 time you picked a red, you'd be inclined to say that 90% of the marbles in the jar are blue. That's basically what experimental probability is all about. Because there's a lot of things we don't know. We have no way of knowing what the real probability would be. So the only way to figure it out is by doing experiments. All right, let's start with 3. Have you gotten into this in your class yet? You should. I mean, your class should follow this curriculum pretty well, right?
Yeah, we've never done probability.
Oh, I thought you had started it already.
No, that's what the advanced class is doing, like the class in front of me.
Oh.
Yeah.
Oh, I misunderstood completely. Oh, so your teacher is telling your mom that if you want to get ahead and work on stuff, that probability would be a good one to start with,
Yeah.
instead of the algebra book, or in addition to the algebra book. I think that you're getting ready to start studying probability. If I remember right, that's what I believe your mom told me, is that she talked to your teacher, and she told your teacher you were working with me, and we were doing fine, and I thought that your teacher told your mom that you were beginning probability in your class, and so that's why we were working on it. Okay, well, this is certainly worth covering here. Whether this is more important than the algebra or not, I don't know. I'm not sure which one you'll get to next. I suspect probability. In other words, I really do believe that in the next week or 2 you'll start probability, so you'll get a little bit of a leg up by us covering it. It's not that hard, though. Let's see what the rest of this chapter has to say. And I don't know. I'm not sure which we should be working on at this point, but we'll stay on probability today. Okay, you have 3 sticks. Each stick has a red side and a blue side. You throw the sticks 10 times and record the results. Use the table to find the experimental probability of the event. So you threw the sticks 3 times. 3 times, 4 times they all came up red. No times did they all come up blue. Twice they came up 2 blues and 1 red, and 4 times they came up 2 reds and 1 blue. So based on this data, what's the odds of throwing 3 red?
If you add them all together, you get 10, and
Okay.
so 4 out of 10 is also equivalent to 2.
Right. Now, you can see what the problem is about experimental probability. Is if you don't have a lot of trials, you get weird results.
Yeah.
There's certainly no reason that you would get 3 reds any more frequently than you would get 3 blues, right? The odds should be exactly the same. In fact, they're about 1 in 8. Let's talk about that for a moment. In order to get 3 blues, or let's talk about the reds. In order to get 3 reds, I have to have the first stick come up red. What's the odds of that happening?
So for the first stick to come up red, you would need it
Just
to have top of the bottom, and so there is 4 each.
hold on. Let's go back a notch. We're going to distinguish between theoretical probability and experimental probability. I'm talking theoretical here for a moment. If you have a stick that's got 1 red side and 1 blue side, and you randomly toss it, what's the odds that it's going to come up red? Just 1 stick.
1 out of 10?
1/2. I'm not talking about this problem anymore. I'm going to get back to it, but I'm just talking probability here. The theoretical odds of it coming up red are 1/2 because it's equally likely to come up red as as blue. Same way that if you flip a coin, it's 50-50 that it's going to come up tails or heads. But that's a theoretical probability. I know that from theory. I don't know it from actual practice. I haven't sat down and flipped a coin 100 times to see whether I come up close to 50 red and 50 black. But I know that the theory behind that, it's the same theory behind this. So to get 3 red sticks, I'd have to have red, red, and red. Each one of them is a half. So for all 3 things to happen, I'm going to multiply these probabilities together. So the probabilities of getting 3 reds should be 1 out of 8. You see where I get that from? Okay. Let's go back and look at a simpler situation. Let's talk about it raining today. If it, say there's a 50% chance that it rains today, and independently there's a 50% chance that it rains tomorrow. Well, if I said, what's the odds that it rains both days, you multiply the 2 probabilities together.
Yeah, you find the average.
No, you multiply them. You don't find the average. In other words, there is a 1 in 4 chance that it would rain both days. Let's think about it. What can it do? It can rain and not rain. It can not rain and rain. It can rain and rain, or it can not rain and not rain. Those are the only 4 things that it can do, right?
Yeah.
Well, only 1 out of those is raining on both days.
Oh.
So it's 1 out of 4. In other words, what I'm trying to get across is that when you have 2 things that have to happen, you multiply their probabilities together to figure out what the probability of both of them happening are. Well, in this situation with the 3 sticks, if I'm going to throw them just once, then the odds of it coming up red, red, red would be 1 over 8. It would be 1/2 times 1/2 times 1/2. So I'm expecting 1 over 8 to be the reasonable answer here. But when I measure these probabilities based on experiments instead of theory, I get 4 out of 10 instead of 1 out of 8. So 3 red is 4 out of 10. What is 3 blue in our problem?
0.
And what should it be?
It should be
1 out of 8, just like 3 reds. In other words, the only way it can come up 3 blues is if the first stick is blue, the second stick is blue, and the third stick is blue. And the probability of each one of them being blue is 1/2. So 1/2 times 1/2 times 1/2. So experimentally, we get 2/5 for 3 reds, and we get 0 for 3 blues. So experimental probabilities are not very accurate. In other words, they don't agree with theoretical probabilities, at least not when your sample size is small, like this case where they're only throwing it 10 times. If he threw the sticks 1,000 times, these numbers would come up a lot closer to their theoretical probability. Let's say he threw the stick 800 times. Well, now 3 red is going to be close to 100, 1/8 of the time. 3 blue is going to be close to 100, and so forth and so on. So when your experiment has enough trials, it becomes far more valid and agrees with theory far greater likelihood.
okay.
Kobe Bryant shoots free throws at about 80%. 8 out of 10. Over the course of a season, which means over the course of a season where he shot 1,000 free throws, he's made 800 of them. It's very good. It's actually about the average of an NBA basketball player. But if you said go shoot 10 free throws, he might only make 6, or he might make all 10 of them if he was just shooting 10 free throws. He might make 8, but in other words, if he's doing just a few of them, he's less likely to hit his theoretical number. We know his theoretical number is 80% because we've recorded it over his entire career. Over 12 seasons, he's shot free throws at 80%. So we know what his theoretical value is. If we're forced to depend on doing it from experiment, we may get a number close to his theoretical, we may not. It depends on how many we get in the experiment. So, to answer the rest of this question, what's the odds of tossing 2 blue and 1 red?
Number 5?
Uh-huh.
2 out of 10.
Yeah, actually number 4.
Oh.
But that's okay. You gave the right answer. 2 out of 10 was correct. Or 1/5. Again, experimental. And what's the odds of tossing 2 red and 1 blue?
4 to 10.
2/5 again.
Oh.
And that's right. 4 out of 10. You said it right.
Yeah.
What's the odds of not tossing red at all? Huh? Based on this experiment.
6.
10 out of 10. Excuse me. Yeah, 10 out of 10. Every throw here produced a red. This one, all 4 of these had at least 1 red, all 2 of these had at least 1 red, and all 4 of these had at least 1 red. So the odds of not tossing a red based on this data is 0. Every toss produced a red, even though theoretically we know it's not 0. The only way you're going to not produce a red is if you toss all 3 blues. Well, according to this data, that never happens. We know that the theoretical odds of tossing 3 blues is 1/8. So the odds of not tossing a red would be 1/8, theoretically. But based on this experiment, it's 0. Yeah, let's continue on probability today. But I don't want to get too far into probability because until you get into it in your class, because I'm not sure how far to go with it.
Well, we're not going to do it in our class.
Not at all. Just next year?
Yeah.
Okay. All right. And that's if you take algebra next year. If my plan works, I don't think you're going to be taking algebra next year. I think you're going to be taking geometry.
I really hope I take geometry.
Yeah. So, in other words, maybe your teacher is telling us that we need to cover probability because there may be some probability questions on the test that you'll have to take to get into geometry next year. But again, I'm not sure how far we should go. We've talked quite a bit of probability here. Why don't we actually table this and go back to our algebra? And then I don't know how to figure out how much probability to give you. Because I don't know how much probability you're going to need to know. What I do know is you're going to need to know all of this stuff, for sure, to pass any kind of algebra test. Do you remember where we left off? It was either solving systems of linear equations
or
linear functions. I don't know that we got to linear functions. Let's see if we got to all of these. Oh, that's right. That was a subchapter. We did graphing, right? We did by elimination. We should have done by substitution, and we should have solved by graphing. Have we done all three?
Yeah. Because we did graphing last week.
Okay. So if I said y equals x plus 5, and then I said another equation is y equals 2x minus 3, how would you solve that by graphing? In other words, our goal is to come up with the values that x and y have to be. And we could do it by substitution, we could do it by elimination. Let's do it by graphing. How do you graph y, the first y?
So, first of all, you want to go on the y-axis,
Okay.
and you want to put a point on 5,
Okay.
put the y-intercept,
Okay.
and then you're going to do rise over run on, so 1 over 1.
So it's up 1 and over 1,
Yeah.
which gives me a slope of about 45 degrees.
Yeah.
So that's the graph of that equation. What's the graph of the second equation?
The second equation, so you want to do minus 3 as your y-intercept.
Okay, I'm going to graph it on the same graph. Okay.
And then you're going to do rise over run.
So it's a slope of 2. So that's about a slope of 2. The solution to the two equations is that intersection, wherever that is on the graph. And that is x equal, let's see, if I solve those two equations, I get x equals 8. So x is equal to 8. And when I plug in 8 for x, y is equal to 13. So this point right there is the point 8, 13. If I had graphed these on grid paper that was accurate, then I could just read my answer off the grid. It would be 8 for x, 13 for y. I couldn't really do that when I graphed it here because I approximated positions. And it isn't necessary that you read your answer from the grid, but it's nice to know that that is an answer to these two sets of equations, is whatever the x and y coordinates are of where they cross.
Yeah.
Okay?
I think that I'm a little bit rusty on the whole substitution one.
Okay, let's go back and review that. We're going to use substitution whenever one of the variables is fully defined. In this case, they're both fully defined.
Yeah, where one...
Right. Well, if y is equal to that and y is also equal to that, well then x plus 5 has to equal 2x minus 3.
Oh, yeah.
That's the way you solve this with substitution. It's really easy when both equations are defined in terms of the same variable like this, because then you can just equate These two things have to equal one another because it's the same y. And then when we solve this, I move the x to the other side, the 3 to this side, and that's how I get x equal 8. And then to solve for y, I plug in x equal 8 into that equation, and I get y equals 8 plus 5, 13. Now, a more typical way would be if the equation was like this, which is the same thing. You there, David?
Yeah.
Okay. If I change that first equation, instead of making it y equal x plus 5, I make it y minus x equals 5, which is the same thing.
So you want to find, you want to convert it to the y equals mx?
No, not necessarily. In other words, I can still use substitution because all I need to use substitution is one variable has to be fully defined. I still have that variable right there fully defined.
So 2x minus 3 minus x equals 5?
Exactly. That's the more typical way to solve by substitution. It is
2y minus x equals 5.
then it would be 2 times 2x minus 3 minus x equals 5. In other words, that's why it's called substitution, is we're going to take whatever y is equal to and substitute it into the other equation. So now we would have 4x minus 6 minus x equals 5, and we would solve that. 3x equals 11, x equals 11 thirds. So substitution is used in two different places. One where one variable is fully defined, and another where both variables are fully defined. Either case, we can use substitution. Elimination is used when, if I want to move this 2x to the other side, and let it equal minus 3, like that. Again, these two equations are the same as the first two that I gave you. I gave you, that was the first one. This one down here, I gave you y equals 2x minus 3, which is the same as this equation. Now, notice that neither variable is fully defined, right? So, since both my y and my x are on the left side, and my number is on the right side, I can use elimination. And I can do it immediately by subtracting the second equation from the first. I don't always have to add them to eliminate a variable. I can do it by subtraction. I'm always allowed to subtract one equation from another. Well, if I take equation 2 and subtract it from equation 1, the y's disappear. Well, what's minus x minus a minus 2x equal to? So this becomes a plus x.
3x.
No, you were right the first time. These two minus signs become a plus, so it really is the same as minus x plus 2x, which is equal to x. And now subtract 5 minus a minus 3.
So would you always be, could you just
8.
subtract
5 minus a minus 3 is 8.
Could you do, like, could you subtract whichever equation from the
Yes, you could. In other words, I could take equation 2 and subtract equation 1 if I wanted to. What am I going to get? Y minus y is still 0. Now what is minus 2x minus a minus x equal to?
Minus x.
Okay. And what is minus 3 minus 5 equal to? Which means x equals 8. So we solved these two equations 3 different ways. We did it by substitution, we did it by elimination, and we did it by graphing. And you want to be able to know how to do all 3 of those for a long time. Those are the 3 primary ways we solve 2 equations with 2 unknowns. And you basically pick whatever method is the easiest given how you're given the problem. Okay. Let me see here. Let's see if there's anything else we can go over here in the last minute or two. Yeah, let's see what they mean by special systems of linear equations. Is that at your house or my house?
Oh, my house.
That was your doorbell?
My sister and my mom just came home.
Okay. All right. Well, we're almost done. In fact, let's practice on these on your own questions here. Oh, this is freaky. You realize how close this is to the 2 I just made up? I didn't look at this when I made up those last 2 problems. Remember what my equations were? Y equal x plus 5 and y equal x minus 3, 2x minus 3. So it's not exactly the same, but it's eerily similar. So how are you going to solve this system of equations?
Both of them are defined. You could use them for substitution.
Okay.
So you do minus x plus 3 minus x plus 5 equals 5.
You set this one equal to this one. Because they're both equal to y. If they're both equal to y, they're equal to each other. Now, what's the problem here? Solve that. What do you get when you solve this?
You get 0x.
Yeah, you get 3 equals 5. What does that tell you?
Impossible.
There's no solution. There's no value of x and y that would make these 2 equations both true. So just because we have 2 equations and 2 variables doesn't mean we always have a solution. Sometimes we don't have a solution. Like this. Whenever you get one number equals another number, in other words, all your variables have disappeared, and you get 2 equals 0 or 3 equals 5, that's telling you that you don't have a solution. Okay? All right. Why don't we end it there? That was pretty good. We actually got quite a bit covered today that is going to be very necessary for you to know. All right. Well, listen, talk it over with your mom, and if you want to do that half hour thing, I can see you after I see Sarah on Monday or before, and then on Wednesday in our normal slot if you like. But think about which you would prefer. I don't really care from my point of view, 1 hour once a week is the same cost as half hour twice a week, and the same time for me. So it doesn't matter to me, but you might prefer it. Just you might prefer only focusing on math for a half an hour instead of an hour. Just all depends on the individual. But if you decide you want to do that, let me know before. We could either begin it next Wednesday or next Monday. But okay. All right, David. You have a good week, and I will talk to you next week. All right. Bye-bye.